Okay, so sure I'm recording here. Okay, packet, related rates packet, page 6, number 3. All right, so helium is pumped into a spherical balloon at a constant rate of 25 cubic feet per minute. Okay, so cubic feet per minute. Any idea which variable that's for? The hint is going to be this cubic feet here. That's right. Yeah. So cubic feet is volume per minute. There's time involved there. And positive or negative? Positive. Yeah. Pumped into the spherical balloon. Okay. At what rate is the surface area of the balloon increasing? What is that asking for? Oh yeah, sure. Well, right. Surface area. We're gonna let S represent surface area, so it'll be ds over dt. But you have the right idea. That's the unknown. Okay. The moment when the diameter is 16 feet. We're really not going to use diameter, but something that's related is radius, right? Radius equals 8. Okay. All right. So that's what's given to us. We're going to go ahead and just find all the derivatives. That we get all the calculus out of the way. Okay, so dv dt. Four-thirds pi stays, it's just the r cubed. Okay, gather information for surface area as well, ds dt. Find the derivative. No product rule here, just power rule. Okay, how's that look? Okay, so let's see here. We're trying to find ds dt. Well, we have r, that's good. R equals 8 feet. We know we can insert that in when we're ready. But they did not give us dr dt. But we do have dv dt. Is there a way to get to dr dt from this information?
Switch ds dt to d.
Well, yeah, that we can't quite do, but maybe there's something else that we can use. So what can we?
Put in 8 for r.
Yeah, put in 8 for r and then put in 25.
Oh, 25.
Good. Yeah. So we have these two pieces, and that will lead us to dr dt, right? Okay. Clean up along the way as well. So it's like a puzzle, right? We're just trying to find all the pieces that fit to get us to our answer. Okay, let's see, 4 times 32, that's 64. I mean, more than that, right? Let's see. 256. Divide that over, get the RTP by itself. Good. All right, so that's the last missing piece that we need.
Are we just leaving it as a fraction?
Yes, yeah, leave your answer in the exact form if possible. Yeah, so we leave that pi there. Either pi will stay in our answer, or we can find a way to cancel it out, which we can do here. Use your calculator. This reduces nicely all the way down to 25 over 4. And what's our unit of measure? Okay, look at this here, surface area. Well, surface area, right? What's area? Area is a two-dimensional unit, right? So square feet. Was that what you said? Yeah, so square feet per minute. Okay, good. All right, page 7. Number 3. Okay, a man is driving north. At a rate of 17 meters per second, he sees a railroad track 20 meters ahead of him that's perpendicular to the road. There's a train going east. On the track, crossing the road, and the man determines with the radar gun. So got the railroad track here, and then while he's still looking ahead, the train has already passed. Okay, so the train going east on the track crosses the intersection, and then he determines with the radar gun that the engine is 35 meters from him. So here's our right triangle. I'm going to, you can label any variable you want. I just like my horizontal being X, my vertical being Y. So that's just my preference. Okay, Pythagorean theorem problem. Okay, how does that look?
Just put, oh, you did the derivative for each, that's what I said too.
Derivative first, yeah. That way we can just get, that we're done with the calculus. We have every variable in front of us. I'm gonna start listing them out, see what I can find. All right, so let's go back to the problem, see what we can gather. Man is driving north at a rate of 17 meters per second. What is that referring to? But every time we put down the rate, we always have to investigate positive or negative. Now he's going north, but think about what's happening here. What's happening to these lengths of the triangle here? But what he's nearing the railroad track.
Oh, so he's slowing down.
Not slowing down. What's happening to the distance between the car and it's getting smaller. So we want to say that 17 represents the fact that the distance between the car and the intersection is decreasing at a rate of 17 meters per second. So this is where it gets students in trouble because they see going north and just you naturally want to say positive, but you always want to imagine, wait, is this length getting smaller or larger? Okay. He sees a railroad track 20 meters ahead of him. Train is going east. The man determines with a radar gun that the engine is 35 meters away from him. And the distance between the car and the engine is increasing at a rate of 5 meters per second. You're right. What do you think? Yeah, distance between the car and the engine. Yeah. Positive because they say increasing. Okay, what is the speed of the train? So we're just looking for dx dt, right? So we do need to find x first, though. How can we find x?
Using the Pythagorean theorem.
Pythagorean theorem, yeah. Okay, good so far. Our final step here. how can we solve for dx dt? Yeah, because we have everything available, right? There's 6 variables. We found 5 of them. We can find that 6th one. Yeah. Use your calculator. Oh, I'm putting the wrong numbers here. Let me know what you get. Mm-hmm. Meters per second. Okay. Okay, so here's the extension for part B. At what rate is the area of this triangle changing? So let's build our area of the triangle first. What's the area of this triangle based off of the variables that I've used here?
Is it not the same equation as the first?
The first one is Pythagorean theorem, which gives us the relationship of the sides of the right triangle. But area of a triangle. Remember the formula for area of a triangle? If you have to guess. So, okay. Yeah, I know that it feels like having to memorize it, but let me ask you this: what's the area of a rectangle? Mm-hmm. So there's a rectangle, right? Here's my triangle.
Times 1/2.
Mm-hmm. Yeah, so it's just 1/2 x times height. I'll use x and y here, so I'll do 1/2 x times y. So if you don't know the formula, just draw it out and you'll be able to convince yourself. Half of a rectangle is your triangle. Now, we want to find, what variable are we looking for here? dA over dt. But to find dA over dt, look at how this is structured here. Obviously, we have to find dx dt and dy dt. That'll show up, but anything else that comes to mind? Is there a special thing we have to apply on the right side?
On the right side?
Before a derivative procedure we have to use?
Power.
Okay, definitely there. Yeah, power rule.
Product rule.
Good, product rule. Yes, recognize the need for product rule there. F prime g plus f g prime. Yeah. Okay, let's go through this list here. Okay, what's f prime going to be?
1/2.
Okay, remember though, everything is influenced by time, so 1/2. X goes to 1, but what else remains? X goes to 1, but there's also, yeah, dx dt, right? Time is going to influence every variable here. Okay. G is just the original G function, G value. F is just the original. Okay, what's G prime? And good. All right, so that's the hard part, just recognizing the need for product rule and then applying it correctly with a related rates context. So now everything that we found from part A is fair game. Enter all that in, we can find the ADT. Let me know what you get. Now, I think it should be smaller because there's a negative here. So we're going to get two values that we're going to subtract. Yeah, dy dt negative.
It can't be negative, right? Area.
Yeah, actually it can be. Because dA dt is not talking about area, it's the rate of change of area. So that just tells us that the area is decreasing, which is okay.
Okay. I got 64.65.
0.65. I've got 0.84, but maybe they were just rounding it differently.
Yeah, I use a smaller number.
Okay. So what's our unit of measure?
Meters squared per second.
Good. Meter squared is for area. Second is for time. Yeah. All right. Page 10. Cone problem. How do you feel about cone problems? How do you feel about cone problems? So. Okay, all right, good. We can get some additional practice then. Okay, so conical tank, vertex down, 40 feet across and 40 feet deep. Okay. Water is leaking out at a rate of 80 cubic feet per minute. What is that? Which variable is that?
The height, or is it volume, dV over dt?
Yeah, because the units of measure is going to give it away, right? Cubic feet per minute. Yeah, okay. Positive or negative?
Negative.
Yeah, leaking out. Find the rate of change of the radius of the water level. What are we looking for?
dr over dt.
dr over dt. When the water is 8 feet deep.
Height.
Okay, put a box around this. We have to keep reminding ourselves we don't want to touch this, right? There's a moment in time. If we enter this in too soon, we're telling the problem that the height of the water is never going to change. Only use after your derivatives have been found. Okay, so here's the hint. The clue is right here. We're looking for dRdt, which means that our volume equation will just naturally have the ability to produce dRdt if only r's remain. So that means we want the h's to disappear so we can get our r to show up. Okay, but we're always going to do our similar right triangle here. Okay, what are the dimensions that I can put onto my diagram? Radius?
Yeah. The radius is at 20.
Mm-hmm.
And then the feet deep. So 40.
Mm-hmm. H and R. Okay, set up your proportion. What would that look like?
Or just putting it back in reverse.
Let's create a proportional equation, right?
So R over 20 equals H over 40.
Mm-hmm. Cross multiply.
40R equals 28. So R equals.
Now, let's think about this. Here's our volume equation. We want the h to disappear, so we want to solve for h. Yeah, we want this to disappear because we are hoping that we can get to dRdt. Okay, solve for h. H equals
2R.
All right, so we're ready to make our substitution, get our volume equation down to one variable. Okay, we have to do our cleanup before anything with derivatives can come up. So how can I clean this up so it's nice and easy for our derivative step? Mm-hmm. And let's put the coefficients together, right? What would that look like?
Over 3 R cubed.
Mm-hmm. Yeah. Good. All right. We're down to 2 variables, which is good. This is nice and clean, no parentheses. We don't have R's all over the place. It's compacted into one term. Coefficients is nicely put next to it. Okay, now we're ready for the derivative. Okay. V becomes? Yes, yeah. I'm going to find a derivative first, and then we can worry about the substitutions. So V becomes derivative. Yeah.
Just 2/3. Or do you keep the pi?
Let's keep it. Let's keep the pi. Mm-hmm.
2r squared.
What's the derivative?
Sorry, 3r
Yeah.
squared.
Okay, is that it? Okay. What happens after I find R's derivative?
I don't know.
Remember, time.
Oh, keep forgetting.
Yeah, right. I know. Every variable is going to have that time component. So times what?
dr.
Yeah, dr dt. Yeah. Okay, let's see what we have. What variable are we ultimately trying to find?
dr or r.
Okay. That's our goal, right? dr dt right there. Okay. That's what we want. That's the unknown. What do we need if we want to be able to solve for dr dt?
R.
Okay, we need R and we need d over dt, which we're good, right? That's good. But is there a missing piece? What do we?
Oh, you could put the height in where the h equals 2r.
Yes, that's right. Yep. We have to find a way to convert the height of the water level to the radius of the water level. We don't want to use the 40 and 40 because these are dimensions of the tank. We want the water information. Good. So that's good. Yep. There's our connection. H. They didn't quite give us the radius, but we had to find it on our own. Okay.
So r equals 4.
Don't reduce that anymore.
Right.
Yeah.
Mm-hmm.
The negative, right? Where does the pi go?
On the top.
Let's stay in the denominator. I know it feels weird in the denominator, but that's where it landed, so that's where it needs to stay.
Okay.
Yeah, otherwise we bring it up, we're changing the answer. Okay, units of measure.
Feet squared. Or
just feet, yeah. Most of your dimensions most of your units will be one-dimensional. Only area and volume, we're going to do something different, but radius, circumference, perimeter, yeah, most everything is going to be one-dimensional. Feet per minute. Okay, so take a look at what we did. How do you feel?
That was better. I could point out my mistakes.
Okay, good. Good. All right. So it's nice to have cone and cylinder right next to each other because we're going to see a distinct difference. Even though the formulas look a lot alike, we are going to explore the difference here. Okay, so number 4. Okay, coffee pot has the shape of a cylinder with the radius of 5 inches. H is the depth of the coffee in the pot measured in inches, where H is the function of time t. The volume of coffee is changing at a rate of negative 5 pi root h cubic inches per second. Okay. Can we start assigning the variable there?
dV over dt
Mhm.
equals negative pi.
Okay. Yeah, feels a little messy because our answer is going to have the h in our answer. We're not going to be able to get rid of h. We just have to do everything and just keep track of that h. Okay. All right, here's our volume formula. Looks a lot like the volume formula for cones, right? Just that 1/3 in front versus just that power squared h. But there's a distinct difference here. Water is going to be dropping. So we know the height is also changing, but what's different between this and cones? What do you notice about
Radius never changes?
Radius never changes, which means that, a lot of students, they want to do similar triangles here. There's no triangle for us to form. We can just make our substitution. Our goal for cylinder is get rid of the r as soon as possible because we can. With cones, we have to take the time to go through similar triangles, but here, radius never changes. There's no need to hold on to it. So what's our radius? 5. Make that substitution. Okay, we clean up our equation. If you look, this is a lot easier to work with than cones, right? There's no parentheses, there's no messiness. But because we do cones so much, we just feel like we have to go through that process as well. But anytime you see cylinder, you should feel, all right, this is going to be easier. Always have to remind yourself of that. Okay, derivative. Anything else? Yeah, there you go. Yeah. h becomes 1, but we got to keep track of h's derivative, so dh dt. Yep, and that's what we're looking for. We're looking for dh dt. We make our substitutions. We will have h left in our answer, but it's okay. They tell us it's okay. So there we go. It says we can have h's. It says our answer will contain the variable h. So what'd you get?
Negative h over 5.
Mm-hmm. What's our unit of measure? Mm-hmm. Mm-hmm.
Way easier.
Yeah, it should be, right? So whenever you see cylinders, you'd be like, all right, I'm expecting an easier problem. I don't want to do any of the messiness involving with cones.
Yeah, that one was a lot easier.
Yeah, yeah. Okay, let's see, is there anything else? Why don't we do one more? You want to do a shadow problem?
Yeah.
Okay. We'll go to page 11 and we'll try example 1. Okay, so man 6 feet tall walks at a rate of 5 feet per second towards the lamppost that's 15 feet above ground. So we're always going to set it the same way, just the vertical components may change. Oh, sorry, 6. And I always like to just label this as X and Y. Okay, we want to set up proportions to begin with. Got a small triangle here and a large triangle here. Okay. So we'll start with the small height. Small height is to the big height as what? Small base is to the big base.
I just call it a square. What is it?
Oh, let's not, we're not going to deal with numbers yet. We're just dealing with
So X and Y.
just X and Y. So how would you write it?
6 over 15
Good, right. We want y to represent the base of the small triangle, and we want the x plus y to represent the base of the large triangle. Okay, cross multiply. Clean this up, combine like terms. Mm. Okay, there's our equation. Derivative is next. What's our derivative? Yeah.
So 6x over 3, 9.
Mm. All right, there's our end of our calculus step. Let's go back to the problem and see if we can start assigning some values here. A man 6 feet tall walks at a rate of 5 feet per second towards the lamppost. Yeah, dx dt. But is dx dt good? Because good, x is getting smaller. Yeah. Okay, at what rate is the length of the shadow changing? Length of this rate, length of the shadow is defined as dy dt. So if you look at the diagram here, the shadow is that y value cast on the ground. Okay, so how do we solve for dy dt?
Plug in -5 and d.
Yep.
So
I got -30 over 9. Oh, you got -10 over 3 is what you said? Yeah. Units of measure.
8 per second.
Okay, part B, at what rate is the tip of the shadow changing? So tip of the shadow, we add the two rates together, dx dt and dy dt.
-25 over 3.
Mm-hmm.
8 per second.
Good.
I think these are pretty easy too. You just have to draw it out properly.
Yeah, once you can do cones, everything feels easier, pretty much.
Yeah, those are definitely.
Yeah, cones are the hardest part. Good, so hopefully that helps.
I think that definitely helps.
Over the weekend, if you have time, go through the test review, or at least do as much as you can off the test review. I have the key on the website, and I also made a video of that as well, but we'll try to get through this on Monday. Whatever we don't finish, we can always do in the help session, but I'll have a help session Monday morning and Monday afternoon.
Okay, kind of the same thing in each.
Uh,
Or is
that's a good question. Yeah, I haven't figured out exactly what I want to do Monday morning. Maybe I'll just pick out some problems that any students want to do, or because this review is 4 pages long, I'm not going to be able to get through this whole thing in class. So I may just kind of pick and choose different ones, and then afternoon I definitely want to do the ones that I'm not able to finish in class. So we'll see what those are.
So I'll try and come in the morning. I can't have.
Okay, good. All right, so if you come in the morning, you can also just tell me which ones you want to do. We can do those. Okay.
Are you on the day of the test?
Yeah, I also have a morning help session going over the morning review, which I'll have that on the website as well.